Okay, now we're going to look at the same function, and we're going to look at the error. For the error, we can expect a bound on the error if we're using Simpson's rule. So we need to formulate this inequality here. So let's go ahead and look at that. Okay. So our error is b minus a to the 5th power. And let's see, let's add again. 180 n to the 4th maximum of the 4th derivative. Okay. Okay, so let's throw in our numbers. We'll have, this thing is equal to, let's see. Yeah, okay, 4 minus 2 to the 5th power, 180 times 4 to the 4th. Now we want the maximum of the 4th derivative. Okay, we're going to pick up that last one. We had f double prime was equal to 6 x minus 1 to the negative 4th power. That's what we got up here. We did that. We're going to continue that down now. Third, negative 24, x minus 1 to negative 5th. And the 4th derivative would be 120 times x minus 1 to the negative 6th. Okay, now we have a similar situation. We want to find the maximum of this. There's an asymptote at 1, and the same thing as 120 over the x minus 1 to the 6th. So it's positive over here, heading down, and it's also positive over here, heading down. So between 2 and 4, we can see that there will be a maximum on this left endpoint at 2. So when x is 2, that gives us our maximum. When you put that in there, you're going to get 120. So that's as big as it can possibly be. So I'm going to put that in there because I have it already. Okay, so that was a 120 right there. So just a matter of now simplifying this fraction. And let's see, we'll take a step here to do that. Okay, I did a little bit of math here. We got 120 over 180 reduced to 2/3. And 2 to the 5th, we wrote that 4 to the 4th as 2 squared to the 4th, which is 2 to the 8th. And then I got that 2 to the 5th over 2 to the 8th to be 2 to the 3rd under here, which is a 2 squared under, which is a 4 times 3. So there's your estimate on the error. That's your bound for the error. You'll never have that more error than that. So your answer will be within 1/12 of the actual answer. That's what that tells us. Plus or minus 1/12 of the actual answer. So I mean, what it's saying is that your integral, your estimate, it will be within your approximation. Let's say this one. The approximation will be less than or equal to, this is the actual, plus 1/12, and it will be greater than the actual minus the 1/12. That's what it's saying. So this is your approximation. Stuck in between here. The actual Okay, anyway, something else I want to mention, that was just one more thing. In that last example, we ended up with an exact answer when we did this. In other words, we use Simpson's rule on this function, and we got an exact answer, which means that the error, if we had calculated the error, we would have gotten a 0 for our bounds. And you can see that because if you were going to take 4 derivatives of that parabola, you would have a 0. In fact, you'd have a 0 after that 3rd derivative. So Simpson's rule, when you're using a quadratic, you know your error is going to be 0. So you will have an exact answer. Because a quadratic might look like this: ax squared plus bx plus c. And p prime would be 2ax plus b. P double prime would be 2a. And p triple prime would be a 0. So p, the 4th derivative of p, would also be a 0. So you see, when you have a quadratic, Simpson's rule, you can see that your error is automatically going to be a 0. This bound will be a 0. So you'll have an exact answer. So, and you can see that'll work with a 3rd degree polynomial also, because your 4th derivative will also be 0 at that point. So if you added one more term on here, for example, let's say dx to the 3rd. As you're differentiating, this would be 3d x squared. Next derivative would be 6dx. Next derivative would be 6d, and the 4th derivative would be a 0. So that would give you the maximum here is a 0 also. So anyway, just a little something to think about there.